Hello, and today's purpose of the day is I can determine how many solutions a system of equations has and describe the system. I can also solve a system of equations using the substitution method. Let's recap graphing systems of equations. Let's look at the terminology, the graph, and the number of solutions for each of the three graphs below. So if we look at the first one, we see here that if we have two lines that intersect one time, that we have exactly one solution. And this terminology to describe this system would be called consistent and independent. And if we wanted to look a little bit further, where the solution would be of this equation would be right there at 2, 4. If we look at the second graph, that actually just looks like one line. But really, there's another line that's there as well, and those two equations form the same line. If the two equations form the same line, that means we have infinitely many solutions, and the terminology to describe this system would be consistent and dependent. The third graph here is two lines that are parallel, which means they have the same slope. So there would be no solution here because those lines do not cross at all, and the terminology to describe this system would be called inconsistent. So if we recap, the word consistent means that there is at least one solution. So as we saw in the first example, when the two lines intersect one time, that's consistent and independent, which means those two lines are independent of one another. They're not the same, and they don't rely on each other. And number two, we also have, at least one solution. Here we have infinitely many. So since we have at least one solution, this system is called consistent. And since the two equations are actually the same line, they're the same, this would be consistent and dependent. Those two lines depend upon one another. And if there is no solution, like the third example, this is just called inconsistent because there's no solution. So let's take a look at these two examples and let's determine whether the solution has a system. If so, let's name it. Then let's describe the system. So let's take a look at number 1. Both these equations are already in slope-intercept form, which makes this very easy to graph. So the first line I'll make in blue, and the second line I'll make in red. So I'm going to go over to my graph at the right and graph these two lines. So I have graphed those two equations over at the right, and we can see that the two lines cross exactly one time. Since they cross exactly one time, this system has one solution, and the one solution is at, appears to us, it's at -2, -1. And again, that would be where the two lines cross, and so if I right where they cross or draw in, it'd be right about there at -2, -1. And then we need to continue and describe this system. So since it has at least one solution, it is consistent. And there is one solution, so consistent, but the two lines are independent of one another. There's not just one line, there's two. So it's consistent and independent. Now let's take a look at number 2. I'm going to graph these equations, and the first one appears to be fairly simple because it's already in slope-intercept form, so I will graph that one in green, and then the second equation here I will make in purple, but I actually have to rewrite this to slope-intercept form before I can graph. So I will move the 8x over and get 2y equals 8x plus 4, divide by 2, so I get y equals 4x plus 2, and so that one will be in purple. And as you can see over at the right, I have graphed the two equations, and there's as best I could, and it appears that they are both the same equation, and we could have actually known that based on what we got for our final answers of y equals 4x plus 2 when we rewrote the second equation and reviewing the first one. So here I have infinitely many solutions. And to describe this system, this would be called consistent because it has a solution, and dependent because the two lines are actually the same line. Now let's look at a few more examples and determine the number of solutions, and let's solve by graphing. And I might even add, let's go ahead and describe the system as well. So number 3, solve by graphing. Again, we're going to have to practice rewriting the second equation to slope-intercept form, so let's do that. So I will subtract 8x and get negative 4y equals negative 8x plus 12 and divide everything by negative 4. So I end up getting, and let's put this right up here, y equals 2x plus 3. So I know that I have the same equation, y equals 2x plus 3 and y equals 2x plus 3. I still want to solve by graphing right now, so I'm just going to graph over at the right just to prove my answer. So since the two are the same line, we have infinitely many solutions. Then how would you describe this system? Good job. It would be consistent and dependent. Let's take a look at the last example. Number 4, we need to, again, solve by graphing. So it appears that both of the equations are in the wrong type of form, and they're very similar. Just the number on the right-hand side of the equal sign is different. That should tell you something just by looking at the two to know how many solutions there will be. But if that answer is not jumping out at you of what it would be, let's go ahead and solve this one together. So I'm going to rewrite both to slope-intercept form. So I've just rewrote both equations to slope-intercept form, and one thing that you can notice about both of them is that they actually have the same slope. So you could have noticed that before you even rewrote them to slope-intercept form. So the only thing different is their y-intercepts. So we know that this will be no solution because the two lines will be parallel. But let's prove that by graphing over at the right. So again, with the graph showing two parallel lines, that confirms our answer of no solution for this system. Let's take a look at another method to solve a system of equations. So now we're not going to graph, we're going to use the substitution method. When we are solving by substitution, we want to first, if necessary, solve at least one equation for one of the variables, either x or y. Step 2, substitute the expression into the other equation to replace the variable. So now you're only dealing with one variable, whether it's x or y, and not both of them together. Step 3, solve the equation, so you'll get your answer for one of the variables. And then step 4, substitute or plug in your answer into one original equation to solve for the other variable. I would always plug that into whatever equation seems a bit easier. Let's take a look at a couple examples. Let's take a look at example 5. First step is we want to solve one of the equations in terms of one variable. We do here have a y equals, so we do not need to do that. So what we can do is we can circle the expression that y equals. So y and 4x minus 6 mean the same thing, and I will substitute that in for y in the second equation and replace y with 4x minus 6. So my new equation will now read 5x plus 3 times the quantity 4x minus 6 equals negative 1. Now I'm going to go ahead and solve this. So I will distribute here the 3 times 4x and 3 times negative 6. So I get 5x plus 12x minus 18 equals negative 1. Now I'm going to simplify and combine 5x plus 12x and get 17x minus 18 equals negative 1. Now I'm going to continue to solve for x, so I will add 18 to both sides and get 17x equals 17. Divide by 17, so x equals 1. But that's only half of my answer. Now I need to go back and I need to look at the original equations, and now I need to plug in 1 into whichever equation I would like. I'm going to choose the easier equation, so I feel that easier equation would be the y equals 4x minus 6. So I would say y equals 4 times 1 minus 6. 4 times 1 is 4. 4 minus 6 is negative 2. So y equals negative 2. So my final answer here, and I'll write this in red, will be 1 comma negative 2. Now if I plug in 1 and negative 2 into both equations, they should make that equation true because this is a solution to this system. So I'm going to go ahead and try that right now just to confirm my answer. So I would say negative 2 equals 4 times 1 minus 6, and 4 times 1 is 4, minus 6 is negative 2. So it works. Here I will type in or plug in 1 for x plus 3 times negative 2 for y equals negative 1, so 5, and then plus negative 6 does equal negative 1, so that works as well. So here would be an example with using substitution to solve this system. Thank you for listening, and please see Schoology for more information. Have a great day. Bye.